recording audio too?
Unit 4, yes. So we have our oxidation numbers of our different elements, including your polyatomic ions. So remember, on the test, you guys will not have the pink one, you guys will have the orange one, but I'm going to use it for a demonstration right now. If you need to get out your polyatomic ion chart because you still have not memorized them, please do so. So, the oxidation number of lead in the compound lead fluoride. I know that chlorine is -1. This needs to equal out to 0 to be neutral, which means the other lead has to be +1. For the next one, I have chlorine again, but there's 3 of them. So 3 times -1 gives me -3. So to balance that out, I would need a +3 on my lead. For the next one, I have lead oxide. So oxygen's -2. To balance that out, I need a +2. Next, I have lead chlorate. So be careful. I have some people who are multiplying by that little 3, and that is unnecessary. So chlorate on the back, we have ClO3. The whole thing has a -1 charge. So this is just a -1. To balance that out, then my lead would need a +1. Questions on oxidation numbers?
Wait, can you do that one?
Yes. So chlorate, this whole thing, is just one polyatomic, which is with a -1 charge. So it's just -1 +1. You don't need to multiply by this 3 when you have a polyatomic. If you had like lead chlorate with a little 2, then yeah, you would need to have -1 times 2 and balance that out with a +2. Yes, sir. Why is it -1? That is an AP standard. You don't need to worry about it. You don't need to worry about why. Okay. Okay, for the next one, it says identify the common polyatomic ions. That's our honor standard. So all of the ones that are starred, please make sure you have those memorized. 4.3, we're drawing our Lewis diagram. So we reviewed yesterday about how to make our basic dot structure. Now we're going to be putting multiple dot structures together. So we have nitrogen gas. Recall that nitrogen gas is one of our diatomic elements. Wrinkle off. So these ones always have 2 of them because they're more stable in nature if they're attached to one another. So for example, if I have nitrogen with nitrogen, I'm going to depict my valence electrons using my dots. Nitrogen is in the 1, 2, 3, 4, 5th column over, so it needs 5 valence electrons. 1, 2, 3, 4, 5. The other nitrogen has the same thing. So I go in a circle to make sure that I can see which ones want to bond. So I have this pair up here on the top that's already bonded, so that means that this one's free to bond, this one's free to bond, and this one's free to bond, and that's exactly what happens. So when your nitrogens come together, the paired ones are on top, the 2 in the center stay together, 2 on the bottom together, and then the 2 on the side. So I actually end up with a triple bond between nitrogen. So that's making it so that that one has 8, and this one has 8, by sharing the 6 in the center. So next I have potassium oxide. This is going to be potassium, which is K, with O. When I write out my K plus O, potassium's in the 1st column, so I have 1 valence electron. Oxygen's in the 6th column, 1, 2, 3, 4, 5, 6. So now I can see that oxygen wants to make 2 bonds, but potassium can only donate 1. So I would need another potassium. I actually need 2. So the formula for this is K2O. So when I go to put them together, I have oxygen with the ones that are already bonded. I leave those alone, or paired. And then I have 1 potassium bringing an electron to this, and another to this. For my next compound, we have boron trichloride, so BF3. I'm going to write out my Lewis dot structure for each one. So I have boron and fluorine. Boron is in the 3rd column, 1, 2, 3. Fluorine's in the 7th column, 1, 2, 3, 4, 5, 6, 7. So I can see that the reason I needed 3 fluorines, because boron wants to get rid of these 3, but fluorine can only take 1. So I would need 3 fluorines to get rid of all 3 of those electrons. So it comes together, I have boron, and then a fluorine comes in on each side with the 7 to make 8. So the reason that this happens is due to our electronegativity value, which is the next section. So when you look at your periodic table, you have the values below your molecular weight. The first one, I have nitrogen. Nitrogen's electronegativity is 3. And that 3 is just a measure of how badly it wants electrons. So the highest one on here is fluorine. It has a 4. So it's basically from 0 to 4, how much does that element want to gain electrons? Electronegativity. So we're going to subtract to find the electronegativity differences, right? That's what this is asking for. So for nitrogen, I have 3.0 minus 3.0 gives me 0. And when I have an electronegativity of 0, that means that they're equally sharing these electrons. They want them both equally as much. So that is a covalent bond when the electronegativity difference is 0. That does happen with every big block, yes. For the next one, I have K2O. When you do the difference, if there's more than one of each element, you do not need to take that into consideration. You just do one of each. So on your periodic table, potassium is only 0.8. So it definitely doesn't want electrons as much as oxygen, which is 3.5. When you subtract these, it's okay that you can get a negative. You just do absolute value. So 0.8 minus 3.5 is going to give me 2.8. 2.8 is greater than 1.7, and when the electronegativity difference is greater than 1.7, that's an ionic bond, which means potassium transferred its electrons to oxygen. So now potassium, by giving away that 1 electron, it becomes potassium plus 1, and it now has the same configuration as argon, which is stable. So it gave away that 1 electron in order for it to be more stable. And the next one, we have boron and fluorine. Boron's electronegativity difference is 2, and fluorine's is 4. It wants it real bad. So we got 2 minus 4 gives me a 2.0 electronegativity difference. That again is above 1.7, so again it's an ionic bond. The times when it would be polar covalent, that would be when you subtract them and it ends up being greater than 0, but less than 1.7. Questions on electronegativity? Okay, next page. I'm going to give you about 30 seconds to complete this sentence properly. It says molecular or ionic bonds are usually strong or weak and do or do not conduct electricity, are volatile, and have a low melting point. Okay, so the key words here that you're looking at are the fact that it's volatile and it has a low melting point. When we did this in the lab, we used paradichlorobenzene mothballs, which was molecular, and we used salt, which is ionic. And when we tried to smell them, the mothballs are really stinky, whereas salt you can't smell. So that means that the salt is holding on to each other more strongly than the other one because it's turning into a gas and getting into your nose. So the one that was volatile was the mothballs, which is molecular. Also, the one with the low melting point, that was the mothballs. It easily melted. Some of you guys sat there for like 3 minutes trying to melt your salt, and nothing ever happened, right? Like, Ms. Rogers, what's going on? So that one is really strong. So the one it's talking about here is molecular. It has a strong bond, and it did not dissolve in water, which means it doesn't create ions, which means it cannot conduct electricity. So it does not conduct electricity. The next question, which was on the Unit 4 test, why do atoms gain, lose, or share electrons? Well, that's just asking you why are these electrons being transferred or shared in order to be stable? And that is because of the octet rule. So, we have the octet rule. They gain or lose electrons in order to have a full outer shell. There are times when a full outer shell does not necessarily mean that it has 8 electrons. When we were doing our board diagram, for example, the inner shell only holds 2, so that is technically full. So even though we call it the octet rule, in a few cases, like helium, or the elements that want to become like helium, boron, beryllium, and lithium, they only end up with 2 in their outer shell to become stable. But all the other ones want to have 8. Okay, we have our honors objective: relate conductivity to electrolytes, their ionic properties in water. So we did this lab. This is just having you remember what happened. So distilled water, as long as it was not contaminated, did not conduct electricity at all, which means it's a non-electrolyte and that it's molecular. So things that do not conduct electricity are molecular compounds. If I look at salt, which is NaCl, when I look at the electronegativity difference of those two, we have a 0.9 and a 3.0. So that's definitely greater than 1.7. So this is ionic. You also know that salt dissolves in water and it conducts electricity just from your everyday knowledge of salt. So this one is definitely an electrolyte, and it's an ionic compound. The next one, we can do the same thing. Al and Cl, when I subtract those, is greater than 1.7. This is ionic, which means it is an electrolyte. The next one, two, they both have H's in them. So this means that they're acids. And acids can be strong or weak. However, that's more of an AP standard. So Luke and Alex in chapter 4, which we'll get to next, you'll learn about the difference for those. However, in general, acids are always electrolytes. They can just be weak or strong electrolytes. Questions on that section? Okay, let's move on then to Unit 4. So remember that in order to be successful, Unit 5, 6, and 7, it's really imperative that you can balance your charges. So that's what we're practicing here. Let's start out with our copper and our sulfur. When we put these together, the question you should always be asking, you should hear my voice in your head, where is it on the periodic table? So when I look at copper, it's here in the center. The rule for when it's in the center means I don't know its charge. It's a transition metal, so I have to have stock number. So this is copper, stock number, sulfide. I have to balance out the charges. Sulfur is -2, so for that to equal 0, this has to be a copper with a +2 charge, so I put Roman numerals 2. The next one. Where is it on the periodic table? Well, sodium's over here on the left, chlorine's on the right. There's nothing special about that, I just name it. This is sodium chloride. And the next one. I've got 2 phosphoruses and 2 oxygens. Where are they on the periodic table? They're over here on the right. C and O are both next to each other. They're non-metals. They're negative. They were never balanced. Don't try to. That's why I just named them using your prefixes. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. So I have 2 phosphoruses. Diphosphorus, dioxide. The next one. Where are they on the periodic table? They're over here. N and O. They're both negative. So I do the same thing. Dinitrogen, pentaoxide. That's very important. Okay, the next one, there is something special about this one. It has an H. When it has an H, it makes it an acid. But remember that there's a difference between having H3P and H3PO4. If I have H3P, when I have H3P, Dr. Barlow, you, yes. I have H3P versus H3PO4. If it has a phosphate attached to it or any polyatomic, you drop the hydro. So this one is hydrophosphoric acid, but the next one, since it has the polyatomic ion, I don't keep that. So it's going to just be phosphoric. Okay? The next one, we've got copper and phosphate. Where is it on the periodic table? Copper is back here in the center, so that's going to be a transition metal. I need my stock number, and then PO4 is just a polyatomic phosphate. So this is copper, stock number, phosphate. So phosphate you should have memorized as PO4 -3. Again, you don't need to multiply by this 4. This whole thing has a -3 charge. So copper just needs to be +3. So this is stock number 3. Next one. We have sodium and phosphate. Where is it on the periodic table? Sodium's over here on the left. Phosphate's a polyatomic, so there's nothing special. You just name it. Sodium, phosphate. Last one. We have iron and chlorine. Where is it on the periodic table? Iron's in the center. That means I need a stock number. So I have iron, parentheses, fluoride, and now you need to balance your charge. Chlorine's -1. There's 2 of them, so that's a -2 charge, which means I need a +2 to balance that out. So this is Roman numeral 2. Okay, for the next section, I'm doing the opposite. So I have iron, stock number, fluoride. So I've got FeS. Then you need to balance your charges. Remember, this 3 does not mean how many, it's your charge. Chlorine is -1 and iron's +3. So for this to equal 0, I would need 3 negatives. So that's FeS3. The next one, I've got gold and chlorine. So AuCl. Gold's +1, chlorine's -1, it's already balanced. Next I have calcium bromide. Calcium Ca, bromine Br. I look at the charges on the periodic table. Calcium's +2, bromine's -1. That is not balanced. I would need 2 bromines to balance that out, so I need CaBr2. Next I have tin oxide. Tin is Sn, and then O for oxygen. When I look at the charges, tin is +3, oxygen's -2, so I need to find my least common multiple of 3 and 2, which is 6. So that means then that I need 2 of my 3s and 3 of my 2s. So that's SN2O3. The next one, I've got an acid, so I need my hydrogen. This is chloric acid, so this is HCl. You should also just have this from memory. We've used this in the laboratory several times. This is just HCl, hydrochloric acid. The next one, I have my prefixes, di and hexa. Do not try to balance these. They're negatives. Negatives will never cancel each other. I've seen people write these out and they spend their entire time trying to take a test making -2 and -3 cancel. It won't ever happen. So I've got nitrogen. There's 2 of them. I've got oxygen. There's 6 of them. I'm done. Move on with your life. Okay, the next one I have potassium hydroxide. So potassium is K. Hydroxide is one of those polyatomic ions on here that doesn't end in H, but it's still a polyatomic. So I've got hydroxide OH -1. So that's KOH. Hydroxide is -1. Potassium is +1. Already balanced. The last one, there's no hydro here. So that means that this has it's polyatomic. So this is HSO4. Make sure it's balanced. So then I have hydrogen plus 1, sulfate negative 2, so that's H2SO4. Questions on naming and formulas?